Okay, so we're going to look at a somewhat looks like involved problem, but it's not as bad as it looks like here. Once we start thinking about things, we have a lot of things that we need to think about, a lot of steps we need to think about here in order to do this. So first off, this is a design problem, and we've got a differential amplifier here, but then notice that instead of having that current source here, we've drawn in the current mirror. Um, with the resistor R1 here, and then we have these resistors RC. So some of the specifications for this design here is that my max power transfer for the, not power transfer, my max power dissipation for the entire circuit is 1.2 milliwatts, and that's when V1 and V2 are equal to 0 volts. So I can have at most 1.2 milliwatts when those are set at 0 volts. Then some transistor parameters are that we have beta is 120, VB on is 0.7, and then another design requirement is that the transistors need to be in forward active mode for a common mode voltage of -1 to 1 volt. So remember, we put the common mode voltage here as far as if we are applying it to these devices here. The common mode voltage, of course, is getting applied to both V1 and V2. So we're saying that either V1 and V2 are both at -1 or all the way up to both +1, and we need to stay in forward active mode in that case. And then we're supposed to design this so that we get AD to be a maximum, and then we're supposed to find resistor values, currents, and AD. Now, it did not specify whether we are doing single output or two-sided output, so we'll compute AD for both. All right, so first let's look at some of these design requirements. First off, we should think carefully here. First off, we know that this here is IREF, and then we've been calling this here with our differential ones, we've been calling this IQ. And now remember here with this current mirror, and beta is big enough that we're just going to go ahead and state that IREF is equal to IQ. Now, in differential voltage, not differential voltage, in common mode voltage, we know that the current splits evenly between these two transistors. So we had IQ over 2, IQ over 2. Now, if I think about this here, just think about this as power being current times voltage. Don't think of all the other components we have here. We have plus minus 6 volts across the entire circuit because we have positive 3 volts and negative 3 volts. I now know what the power dissipation across each one of these has to be because I know that IREF is equal to IQ. So I know that here I'm going to, actually what I'm going to do, instead of doing dotteds, I will do solid here. This here, this circuit element here has 6 volts dropped across it, and then this circuit element here, or combination, has 6 volts dropped across it. But if I think about it, these have the same current. So this is IQ going through the green circuits, and it's IQ going through the red circuits. And we have 6 volts dropped across each of them. So the power would have to be 0.6 milliwatts for the the red portion, yellow, and then P would have to be 0.6 milliwatts for the green portion, because that's just the way it is when we have common mode voltages. We know that those currents split evenly, and then current mirror, we're just getting IREF is equal to IQ there. So let's erase some of these circles here and go ahead and start looking at what that gives us here. Well, then I know since power is equal to current times voltage, if I think about where the red current loop was, I have 0.6 milliwatts has got to equal 6 volts times Iref. Well, that just gets me real quickly here that Iref has to be 0.1 milliamps. Okay, well that's pretty straightforward. And now getting what R1 is that's just a straight computation here, because remember here that Iref is equal to V plus minus VBE on minus V minus over R1. In other words, R1 is going to be equal to 3 minus 0.7 minus negative 3 divided by 0.1 milliamps. So if I do that computation here, let me pull my calculator up and do that real quickly. And I get 53 kilo ohms for R1. And so we've got one of my resistor values now. So let's go back to the circuit here. So I know now my design here, this is a 53 kilo ohm resistor, and that's going to get me a 0.1 amp current. And if you want to just go ahead and double check, of course, you can do 6 minus 0.7, 6 minus 0.7 divided by 53,000, and we get 0.1 milliamps. Alright, so we get that one. Now, that also means now what do we have here? That this is equal to 1 milliamp. This is equal to 0.1 milliamps, right there. Now we need to figure out what RC is. Now the key thing here is to figure out what RC is, and it's kind of hidden here on how we have to do this. And we have to go back and remember even how we keep things in forward active mode. Okay, so we've got this VCM here. Okay, so it's got to be between -1 and 1 volt is what that input is. But then what I really need to figure out is, what is this voltage here? What is VC? Because I'm still in the V1 equals V2 equals 0 case here. Oh no, not equals 0, but I'm still in this, the idea that I have to satisfy this condition. Well, what do we have here? Well, remember that, of course, we have to have this junction forward biased at 0.7 volts. And that will just happen with our current mirror setting up. As long as we have everything set up properly, that will just naturally occur for us. But then what do we need here for this junction here? And so remember, this is the base collector junction. And this is where we have to remember back here. The base collector junction must be reversed bias for transistor to be in forward active mode. So we think about it, what does this have to be there? Well, this input here could be anywhere from -1 to 1 volt. And reverse bias just means, of course, that it's less than 0. So we need to have VBC be less than 0. Well, if VB was equal to -1 volt, then VC would have to be, well, we'll let it be less than or equal to 0 volts just for simplicity. Then we'd have -1 minus VC has to be less than or equal to 0. In other words, VC would have to be greater than or equal to -1 volts. Okay, but now if VB is 1 volt, then 1 minus VC has to be less than or equal to 0. So VC has to be greater than or equal to 1 volt. Okay, so which condition do we have to apply? Well, it's got to satisfy both of these. So we have to choose that VC is greater than or equal to 1 volt. So what are we going to do? Well, we're going to just make it at the smallest possible here. So we'll set smallest possible. The reason is because then that gives me the largest voltage drop across RC. Why would I want the largest voltage drop across RC? Well, the bigger RC is, the bigger the gain is that I can get. So I'm going to let this be here, VC. I have to make it at least 1 volt. So I'm going to make it 1 volt. I could make it 2 volts, but we'll see in a second here why you wouldn't want to do that. So if we make that one here, so we set VC equals 1 volt, and then simply, well, RC is going to be 3 minus 1 volt divided by, well, we got to be a little bit careful here. It's not going to be 0.1 milliamps, it's going to be 0.05 because the current divides evenly between those two branches in common mode. And so if we do that, we get 40 kiloohms. Oops, forwarded up too far here. So these would both be 40 kiloohms. I'll just erase the RC. So our design is done at this point because we have the resistor values and we have the currents. The currents we already computed. We have the IREF is 0.1 milliamps, IQ is 0.1 milliamps, these currents would be 0.05 milliamps, and the resistors are 40K. Now all we have to do is count the differential, compute the differential voltage gains. Now I didn't say which one it's going to be, so we're going to do for both two-sided, which is the equation right here, and for one-sided, which is the equation right here. So for two-sided, the differential voltage gain is IQ times RC over, and I believe it was 2 VT. Yeah, 2 VT. Which would just be 0.1 milliamps times 40K over 2 times 0.026. And if I did my calculator correctly, I would have gotten the right answer. There we go. I get 76.9 for a two-sided. And then a one-sided we'll see is going to be, well, exactly half of that. Because it'd be IQ times RC over 2 VT, not 2, 4. So this would be 0.1 milliamps times 40K over 4 times 0.026. Which, if we do that and actually multiply it out just to be certain, we get, of course, half of it, which is 38.4. Well, and since I computed, I got 4.6. All right. Now, these would, we're done with the problem, but we can talk a little bit more on why did we want to set VC to be the smallest possible voltage we needed. You might say, well, why didn't I set it to be -1? Because VC has to be greater or equal to the -1, and VC has to be greater than or equal to 1. Well, I can only, only way to make it is greater than or equal to 1, so set it equal to 1. But for instance, if we had set suppose we chose to set VC to 2 volts. Well, then RC would simply be 3 minus 2 volts over 0.05 milliamps, which would get us 20 kiloohms. But we can see right away here what's going to happen. That's not going to give me maximum differential gain because RC here is directly in my equation. So I want to set RC as high as possible in order to get the most amount of gain out from this circuit. Now the other thing here we should note here, just kind of going back to our ultimate goal here, is see again how the gains here, even if you're doing a two-sided output, two-sided or one-sided, the gains aren't that high. And we need gains to be in the hundreds of thousands for our operational amplifier. So again, if you think about what we're going to need for an op amp, believe it or not, we're actually pretty close to a basic op amp just with this circuit right here. All we would need to do is add on a gain stage and then an output stage. And the output stage would basically be to lower the output impedance of the amplifier, because op amps tend to have a relatively low output impedance. And there's reasons for that, of course. But this problem here, of course, gives us a little bit of a design problem. And I like this problem just because it kind of combines a lot of what we were learning. And while it looks like there's a lot going on here at the beginning, hopefully you all agree that once we dove into it, it was actually pretty simple and straightforward to compute all the values we needed.